Okay, on this next problem, we're going to deal with compositions. It's very similar to the previous one. And again, it's a proof or disprove. And I'm going to do only parts B and C. So, again, whether or not you should prove or disprove, you sort of have to think about it and see if you believe it or not. Again, I cannot give you more advice than I gave you in the last video. So if you think about this enough, or if you try it, this one we can prove. So let's prove this. Alright, so this is a containment. So here I'm going to do something that you probably shouldn't do when you're writing things and use just logical symbols in here. Do an if then, if then, if then. But I'll say a word about that, why I'm doing that. So in general, you shouldn't do that. If you're doing an exam, so maybe you should ask. Because in principle, is right. And if you use the logical symbols, and that is fine. But at some point, you have to learn, it's part of this course, to learn how to write proper proof in English and everything. And you never publish something that has just a bunch of logical symbols like I'm going to do in here. But it is right, and it shows what you're doing in any case. So you should ask, can I do like, using just the symbols or not? But okay, I'll do like that, these and there, but there's a reason for that. So we start with an arbitrary element of the first. Now again, you can think of what is an arbitrary element in here. So R goes from A to B and S and T from B to C. So I have to start with an element AC in here. And I have to show that this element is in the second. So this implies, so I'm going to use, that's what I was saying, I'm going to use these sort of implications in their if-thens. What? So by definition of composition, it implies there exists some B in capital B such that A, comma B is in R and B, comma C is in the intersection of S and T. So this is simply the definition of composition. Now this implies, by definition of the intersection, that is in both. So there is a B in B, so I'm just copying, such that AB is in R, BC in S, and BC in T. Okay, so sorry about the little breaking there, but I had to add it a little bit. But here, what we can do, we can apply the definition of composition. So what happens? Because AB is in R and BC is in S, by definition of composition, what I get is that AC is in the composition of S with R. And because AB is in R and BC is in T, in the same way, I get that AC is in the composition of T with R, right? Because of the existence of this element in the middle there. So, by definition of intersection, we get that A, comma C is an intersection of S composed with R and T composed with R, which finishes this part. Right? We took an arbitrary element of the first, and it is in the second. Right? So that's how we prove containment. Okay? All right. So the next part is again to prove or disprove part C, and if you look at it, it's the exact same two sets that we had before. Now, you probably shouldn't do these because this is not how things work in real life, but if you were to guess if this is going to be a prove or disprove, you'd be very inclined to think that this is a disprove statement. Or a statement to be disproved, I should say. Why? Because otherwise, there's no reason to ask for B. You can ask only for C. C implies B. Implies both containments, the first containing the second, and the second containing the first. Okay? So you'd be inclined to try to disprove these instead of trying to prove. But again, this is not fair. I mean, it's a hint that you might not get in an exam or in real life. So let's think about this for a second, okay, instead of going straight into trying to disprove these. We can try to prove it, and like I said, maybe this is going to give us a hint of what is going wrong in there. Okay, and maybe that's going to help us to cook up a counterexample. Alright, so let's see. If I were able to prove these, I probably should be able to reverse all the arrows in here. And that's why I use the arrows instead of writing things down, because then I can just, you know, if I can go back, I have if and only ifs everywhere, and I prove the equality. Okay, so let's see if we can reverse all the arrows. Let's look at the first one in here. So AC is this intersection. Well, that's the definition, right? If AC in the first, N is in the second. So definition always goes both ways. So we can replace this if then in here with an if and only if. Alright, so then comes in here. So at this point it might be a good idea to perhaps pause and think about it for a second before I tell you the answer. But, well, what's happening? So here what I did, if you remember, I applied the definition of composition. Well, and I told you many times the definition is always if and only if. So you might say, this is indeed reversible. But you have to be a bit careful. We use this definition twice. And there's a little catch in here. Because to say that A, C is in S composed with R is to say that there exists a B such that AB is in R and BC is in S. So it seems to be matching. And there exists a B in capital B such that AB is in R and BC is in T. So it seems to be working. But this is not correct. Again, maybe you can pause now and think about why this is not right. The reason is, conceivably, when I apply the definition for this first, I would get a B1 that works for both. And I want to get a B2 that works for the second one. There's no reason why the same B should work for this definition, for this composition, and work for this one also. Perhaps I need two different B's, a B2 for T composed with R and a B1 for S composed with R. So this is indeed exactly the problem. This is where things fail in here. So I cannot reverse this arrow. Like I said, sometimes by the way, this arrow here, if you have this statement, which we don't, we cannot go back, but if you have this statement in here, can we reverse it? Well, yes, so in here we just use the definition of intersection, so these would be reversible, and these we just use the definition of composition, so these would be reversible. So the only one that fails is this one in here. So somehow we should play with this fact in here, that there should be two different B's that would work. Okay? So what I want is an element in here that I can get with different middle elements. So this was exactly my idea, and so here is the counterexample. So this is false. Counterexample is below. So you can take R to be 1, 2, 1, 3. Take S to be 2, 1, and take T to be 3, 1. Okay, so I'm trying to cook up the middle elements, which is different. A B1 for S and a B2 for T. Now, what happens in here? So what is S inter T? Well, there's no common element, so this is empty. So S inter T composed with R is also empty. There's no element in this composition because there's nothing here. How about the right-hand side? What is S composed with R? You can actually compute this in this case, since I took very small relations. Remember, relations are just subsets, so these are relations from Z to Z. A, B, and C can take all of them to be Z, the integers or natural numbers or real numbers, whatever, have 1, 2, and 3. Now, what is this? So since this is such a small case in here, these are the elements that are compositions, but the only composition that I can make with R and S is with a 2 in here, right? And this gives me 1, 1. Okay? So that's, in concrete examples, that's how you make compositions. You look for a second coordinate in the first set that is the same as the first coordinate of the second set. And then you compose them. This one is this, and this one in here is this. And what happens if you do T composed with R? Again, you cannot compose 1, 2 with 3, 1, but you can compose 1, 3 with 3, 1, and then this again gives you 1, 1. So when you take the intersection of those, well, it's the intersection of a set with itself, which is itself, and of course, this is not empty. Okay? So they are different. So this does not always happen. Okay? And again, my idea to come up with this counterexample came from this realization in here. That's what was wrong. Remember that I could have different B's. So that's what I cooked up in there, different B's. Okay? Giving you the same element. Okay? So have the same composition. So this is in both. But to get this 1, 1 in here, you had 1, 2. To get this one in here, you have 1, 3, 3, 1. So B was 3 in here. To get this 1, 1 in here, I had to use 1, 2, 2, 1. So B here was 2. Okay? So that is it for this problem. So again, coming up with counterexamples can be challenging. You need a little bit of reasoning, a little bit of practice, understanding of all the symbology. It's one of those things that you cannot just get away by writing down definitions and moving symbols around without understanding them. Okay, so I like these examples. They can be challenging, but they really test you and pushes you to understand things better. Okay, so that's it for this problem 12.